In this video, I sort of wanted to explain, we've learned a little bit about various cues that insects use. I wanted this video to be a bit more experimental, to focus on how we would do this in the context of a research setting. I borrow a couple of images that I actually made during my PhD for one of my PhD chapters because I did spend a fair amount of time just observing behavior. So, you make these assumptions that insects are responding to a variety of cues in their environment, from visual cues to chemical cues. But how do we actually measure those behaviors? Now, in an earlier part of the course, you might be familiar with olfactometers, which are dedicated sort of devices to measure responses to purely chemical cues. But there are other ways in which we would measure other cues, like visual cues. What do we actually measure? So some experiments, like the one you see here, would be sort of like a typical flight arena. And you'll notice here's a very, very simple sort of setup where it's like a meshed cage, and then you can view the insect from all sides or one side. You can modify the conditions of the room that you're doing this experiment in. So you can turn off the lights, turn on the lights, whatever, right? So there's many ways in which you can simulate the environmental condition. In this case, this is the sort of setup you would use if you were dealing with insects that perhaps were very, very weak flyers. And so in this case, this is the diamondback moth that many of you are familiar with, and they're not a very strong flyer. And so you wouldn't necessarily equip this cage with any sort of like, I'll talk a little bit more about wind tunnels very shortly, but it wouldn't be anything that causes too much of an air current because you won't be able to see the natural behaviors, so to speak. What I did want to say is you'll find in the literature many people who work in this space tend to just put a plant in a pot, in a cage, and then just measure something and observe something. And that's great. But in an applied setting, in an agricultural sense, people don't grow crops in pots, right? So we built this arena that was flushed to you want to have your plants flush to the ground. And so it was built with an arena with a platform with which a pot could be inserted so that on the platform where the moths responded to, it was flushed with the soil surface of the plant. And I also took the time to vary some of the platform colors. So of course you could do a stock standard white one, but then you can also put a brown color platform, a green color platform, just to see if these moths are eliciting behaviors as a result of color contrast. Now, in terms of the actual measurement, there are a few things that you could measure in an insect like the diamondback moth. So we would typically categorize behavior when we think about insect-plant interactions to the pre-alighting phase and the post-alighting phase. So you hear these terms very frequently. So we briefly talked a while ago about arrestment. So you see on the right there, right? So arrestment is just that fancy way of saying landing. It's a weird way, right? Where you say, oh, a cop comes to arrest you. In a weird way, it's kind of like grounding you and confining you. So arrestment in the context of insect behavior is landing. So you can see here that you can have some arrestment. Then another measurable behavior then is really cute with diamondback moth. They never ever it's really weird. They never really concurrently rotate their antennae. It's almost like one at a time usually, but that already tells you that they are sampling the headspace in their vicinity to verify if there's a host plant nearby, and then that elicits the next round of behavior. Now, what that tells us is that the visual cues are limited. Not surprising given that this is an insect that is typically active in the evening, right? Or early morning. So visual cues are really broad sort of cues that they use, and it's the contrast of green against non-green that causes the insect to alight, because it goes, okay, there's a plant nearby, it's somewhere in this vicinity, I'll save energy, I don't need to fly anymore, don't need the winds to take me away suddenly. And then once I land, I will sample the air and I will proceed towards where there's a greater concentration of the cues to which I'm attracted to. In order to then maximize my chance of finding a plant, it's not uncommon for diamondback moths to hop. While I'm here, I'll also note that this is a female. You can see that the abdomen is swell and full of eggs. And then they can hop. And then there is fine scale intonation where they can drum the ground, sort of like hit their antennae towards the ground. And then a variety of mechanisms to actually get onto a plant. And in this context of some of the research that I did, there were very conservative ways in which the insect would typically land on the plant. Now, if you have a strong flyer like butterflies or some of the larger moths, then you would move to an option where you have a larger arena for them to fly, and you would also go in with what we call a wind tunnel. So here's an example of a wind tunnel. We also have a couple of these at UQ, and I've also done experiments on them before with larger moths. I've worked with Helicoverpa and the cabbage white butterfly Pieris. And one disadvantage of this is that if you are also making the assumption that these insects are responding to audio cues, which is really just mechanical vibration. These are a problem because wind tunnels are bloody noisy. They're really, really loud. But the theory with wind tunnels, and there's a huge amount of studies done with wind tunnels, is, if we start from the right moving towards the left, you are drawing air in, okay, from the right into the wind tunnel. So the direction of air is moving from right to left in this particular diagram. And you want to make sure that the air is filtered, typically with activated charcoal, to remove as much odors from the air to begin with, so that the air that's entering the wind tunnel is as clean as possible. You would then put your cues, whether that is on a dental wick or a plant, whatever, right? So you put your chemical cues close to where the clean air enters. And so the theory is that the clean air is drawn from right to left in this image, and it is drawing cues downstream, and there's a concentration gradient as we move from right to left. You will release your respondents, your insects on the left, and you will observe their behavior. And they will fly towards the cue. And there are many ways you can design the experiment, whether it's a preference experiment or whether you're measuring the length of time they exhibit certain behaviors, so on and so forth. And you will often find with a lot of studies that work in wind tunnels that there's also a lot of non-respondents. So it's nice to try and query why that is, because the reality is that the wind tunnel, being so noisy and technically such an unnatural space, has its limitations, which is why you often find people that work with, trying to work out long distance cues used by insects use maybe far more sophisticated experimental techniques in this day and age.